All right, physics students, today we are going to begin our tour of the big four kinematics equations. So there are four equations that you're going to be using on this assignment and the next assignment, and really for assignments for about the next 3 to 4 weeks. And these are called the big four kinematics equations because they can describe lots of different types of motion, and we use them in different ways. These are all derivatives of, and I don't mean that in the calculus way, but they are all derived from a couple equations that we already know. And I'll go through the derivation at the end for those who are interested and who don't want just equations dropped out of the sky on them and wonder where they came from. But this is the homework that I'm assigning today. And it's page 45, number 1 and 4, and page 49, numbers 2 and 4. All right, so page 45, number 1, it says, as the shuttle bus comes to a sudden stop to avoid hitting a dog, it accelerates uniformly at negative 4.1 meters per second squared as it slows from 9.0 meters per second to 0.0 meters per second. Find the time interval of the acceleration for the bus. So what do I know? All right, this is where we start filling in a variable chart, and it goes like this: V, V naught, A, delta X, and T. And I just make the chart like this. Now I'm gonna know some of these things, some of them will be unknown, and some of them will be neither known or unknown. So it says, as the shuttle bus comes to a sudden stop, that is V. That is my final velocity. Now you might be saying, why don't we call it VF? The truth of the matter is, at the beginning of the chapter in this book, it does, and then it just shifts to being V. It's magic, I don't know why, but this is how we do it. Then V naught is our starting velocity. Now this one, it says it doesn't. It says that it slowed from 9.0 meters per second to 0. So the initial was 9.0 meters per second. And it says that the acceleration in this case was negative 4.1 meters per second squared. All right, now it says find the time interval that it took for that to happen. Okay, so notice it doesn't say how far did it take place in. All it cares about is these 3 known variables and this unknown. This covers steps 1 and 2 in the 5-step problem solving process. So what I look at here, and the reason I made this chart this way is so that I can now, I've got the first, second, third, and fifth thing. If I look at my chart right here that I made in the notes, first, second, third, fifth, this is the right equation to use in this situation. So now step 3, writing down the correct equation, V equals V naught plus AT. All right, I want to solve for T. So I'm going to move V naught over to this side. So now it becomes V minus V naught equals AT. And I'm going to divide both sides by A. And so now I have T equals V minus V naught over A. All right, and now I'm on to step 4, plug in the numbers. V is 0, V naught is 9, and A is negative 4.1 meters per second squared. Again, that equals time. So now I get out my calculator, and I go negative 9, because 0 minus 9 is negative 9. Negative 9 divided by negative 4.1 equals 2.195. So I'm just going to round that to 2.2. T equals 2.2 seconds. So that's how fast the bus stopped. All right, let's move on to number 2. All right. Okay, on to number 4. Turner's treadmill runs with a velocity of negative 1.2 meters per second and speeds up at regular intervals during a half-hour workout. After 25 minutes, the treadmill has a velocity of negative 6.5 meters per second. What was the average acceleration of the treadmill during this period? So you might be saying, I have no idea where to start. This is where you start. V, V naught, A, delta X, T. Okay? you write this down every single time because it matches up perfectly with the notes. All right, and it will help you. So it starts out with a velocity of negative 1.2 meters per second. It goes up to negative 6.5 meters per second, and it takes 25 minutes for that to happen. And the question is, what is the average acceleration? It doesn't say how far do you go or anything like that. All right, now before we get started here, notice that our time is in minutes, and so we need to convert that into seconds first. So x seconds equals 25 minutes. 1 minute equals 60 seconds. So 25 times 60 equals 1,525 seconds. Okay, so that's my time. All right, now, again, let's take a look at our chart. What do we have? I've got a velocity, an initial velocity, an acceleration, I don't know, but it's part of what I'm trying to find, and I have time. So again, equation number 1. V equals V naught plus AT, and we want to solve for A because that's what we're trying to find. So V naught will come over. When it does, it becomes negative. And then I divide both sides by time. And then we just plug in our numbers. So V, negative 6.5, minus V naught, negative 1.2, over 1,525 seconds. Negative minus a negative, that becomes positive. So this is negative 4. Let's do the math here. 6.5 minus 5.3, so negative 5.3 on top, meters per second, over 1,525 seconds. All right, so then I go negative 5.3 divided by 1,525, and I get 0.0035, negative 0.0035 meters per second, right? Now that might not be, I mean, we're keeping everything in seconds. That's a really small number. I probably could have kept the time as minutes and then gotten a little bit bigger number, and then it'd be, this is how many meters per second per minute it changes, but either way is correct. I would say pay attention to these units as well. Meters per second, it's like that's how much, what the units of velocity change by every second. Sometimes it's written like this, meters per second squared, right? And you might say to yourself, well, where does that come from? That comes from meters per second over seconds, which is like seconds over 1. Well, if I have two fractions and I divide them, it's like multiplying by the reciprocal. So that becomes m over s times 1 over s, and that leads us to this, m over s squared. All right, let's move on to page 49, number 2. All right, page 49, number 2. When Maggie applies the brakes of her car, the car slows uniformly from 15 meters per second to 0 in 2.50 seconds. How many meters before a stop sign must she apply her brakes in order to stop at the sign? So same thing, V naught, A, delta x, T. And it says she slows from 15 to 0, so her initial velocity is 15, her final velocity is 0. It does not tell us an acceleration, it just tells us a time, 2.50 seconds, and it asks us how far does she travel during that time. So now, I want to look at my chart here, and I go, okay, I've got V naught, nothing for A, so here's an empty space for A. Delta X and T are both spoken for. So this is the correct equation for me to use, equation number 2. Delta X equals 1/2 times V naught plus V times T, all right? And then I can just plug my numbers in, 1/2 times 0 plus 15 times 2.5 seconds. Let's get out the handy dandy calculator here, and we go 0.5 times 15 times 2.5, and I get 18.75. That's 18.8 meters. Seconds canceled out seconds there to leave me with meters. All right, and then finally, number 4, 49, number 4. Okay, page 49, number 4 says, a car enters the freeway with a speed of 6.4 meters per second and accelerates uniformly for 3.2 kilometers in 3.5 minutes. How fast in meters per second is the car moving after this time? All right, so let's fill out our chart. And I've got, it enters the freeway at 6.4, so that's the initial velocity. And it accelerates uniformly for 3.2 kilometers, so that's a displacement. And it does it in 3.5 minutes. And the question is, how fast in meters per second is the car going after that time period? All right, so here we've got meters per second, here we have kilometers, here we have minutes. We're gonna have to convert all of these into meters per second because that's what it wants for the final answer. So before we do any math, let's take care of that. 3.2 kilometers, remember a kilometer is 1,000 meters, so this becomes 3,200 meters. And then time, 3.5 minutes, we want that in seconds, so x seconds equals 3.5 minutes. 1 minute, 60 seconds. So 3.5 times 60 equals 210 seconds. So that's our time. Okay, so what do we have here? Well, it's the same as the last problem. We have v, v naught, delta x, and t, or else one of those is an unknown. But there is no acceleration in this one. We don't want to find out. We don't know what it is. So again, it's an example of using equation number 2. So delta x equals, now let me just start that over. Delta x equals 1/2 v naught plus v times t. And we want to find v this time. So let's rearrange. Let's get rid of this 1/2 first. I'm going to multiply both sides by 2. I want to get rid of this t. Right now it's being multiplied, so let's divide both sides by t, do the opposite, all right? So let me rewrite this a little neater. 2 delta x over t equals v naught plus v. And I want v all by itself, so if v is being added right now, let's just subtract v naught from both sides. I'm just gonna move it over, so it becomes 2 delta x over t minus v naught equals v. So now it's time to plug in our numbers. 2 times 3,200 meters over 210 seconds minus 6.4 meters per second. All right, and then, again, I'll take out the calculator. 2 times 3,200 equals 6,400 divided by 210. I have to do that first. 30 minus 6.4 equals, and I get 24.1 meters per second for my final velocity. Okay, now on to the derivation of these equations. If you don't care, you can check out and move on with your life. If you're like, I want to know where those equations came from, let me go through this. And I'm going to go kind of quickly. I already wrote it all down, but here are the equations we started out with. V equals delta x over t. We talked about that last week. A equals v minus v naught over t. This is the acceleration equation. And then we also have an equation for average velocity where you take your starting velocity, your final velocity, you add them together and divide by 2 like you would do with an average. This only works when you have a constant acceleration, meaning that it's a nice smooth curve going up. All right, you're not starting and stopping and starting and stopping. This equation would not work for that. Okay, so we start out with these three equations. V is the final velocity, V naught initial velocity, A is acceleration, and T is time. Okay, and again, this is the acceleration equation. So this equation here actually is equation number 1 of the big four. We take that equation, we solve for V, but we just rearrange. So that's equation number 1. That's where that comes from. All right, equation number 2. So now we look at two of those equations we started with, our average velocity, where you add the first and the last and divide by 2, and average velocity is your displacement divided by time. Well, if both of these things are equal to your average velocity, then they must be equal to each other. So V plus V naught over 2 equals delta x over t. If we cross multiply and solve for delta x, we get delta x equals 1/2 V plus V naught times t. This is equation number 2. That's the one we use in the homework today. All right, equation number 3. Okay, where does that come from? So let's take equations number 1 and 2. V equals V naught plus AT, and delta x equals 1/2 V plus V naught times t. All right, so if I take this V naught plus AT and I substitute it in just for that V right there, I get this. Okay, see how that V naught plus AT used to be that V. I then simplify. V naught and V naught go together, so now I have 2 V naught. I also multiply t throughout this whole thing. There should be another t right here. Oh, no, that's not right. No. Then I multiply t through, and I get going from here to here, I multiply 1/2 times what's inside the parentheses. 1/2 times 2 is 1, so I just end up with V naught. 1/2 times AT becomes 1/2 AT. The last step, I take that t and I multiply it by both of these terms. I get V naught t plus 1/2 AT squared. And that's equation number 3. And finally, equation number 4. I take equations 1 and 2 again, but this time, instead of solving both for V, I solve both of them for t. So V plus equals V naught plus AT becomes t equals V minus V naught over A. Delta x, I rearrange here, I get 2 delta x over V plus V naught. So because both of these things equal t, they will equal each other right here. And then cross multiply again. And I simplify. Here, this is like a factored quadratic. So use the FOIL method, V squared minus V naught V plus V naught V minus V naught squared. These two cancel out. This is negative V naught squared. That moves across the equal sign to become positive V naught squared plus 2a delta x equals V squared. This is equation 4. If you would like a further explanation, I'm willing to explain it further. All right, thank you.